All right, in 6.3 part 1, we are going to look at double angle and power reducing formulas. Okay, the whole section has half angle formulas as well. But let's start by deriving the double angle formulas from the sum formulas that we already know in the last section. Okay, and we didn't derive the sum formulas because that is a little bit longer proof, but the book has a good explanation of those. But let's go from the sum formulas to the double angle formulas. So for this, what I want to assume is that u and v are the same angle. So what I'm going to do is just make both of them x. Okay, so this will be sine of x cosine of x plus cosine of x sine of x. So here, inside of the parentheses, x plus x is just 2x, right? So we have sine of 2x equals, now these are the same term, right? It doesn't matter since we're multiplying that these are flipped. Sine times cosine is the same as cosine times sine. So I can say I just have two of these, right? 2 sine times cosine. So this is our first double angle formula. Okay, sine of 2 times some angle equals 2 times the sine times the cosine of that angle. Okay, we can do something similar for tangent as well. If I take my sum formula for tangent and assume that these are the same angle, so tangent of x plus x, then that'll be tangent of x plus tangent of x over 1 minus tangent of x times tangent of x. And that would just simplify to tangent of 2x equals 2 tangent of x in the numerator. Right, I've got two tangents. And then the denominator would just be 1 minus tangent times tangent would be tangent squared of x. So this is my double angle formula for tangent. And then finally, do the same thing for cosine. If I make the angles the same thing, cosine of x times cosine of x minus sine of x times sine of x. So cosine of 2x equals, this would just be cosine squared minus sine squared. All right. Then there are a couple other forms of this. Okay, so those other forms just come from using a Pythagorean identity. Right? We know that cosine squared plus sine squared equals 1. So what we can do is take this and replace cosine squared with 1 minus sine squared. And if I were to take this and subtract sine squared over, I could say that this is 1 minus sine squared, and then minus sine squared again. So that could just be 1 minus 2 sine squared. Similarly, if we subtract cosine squared over and make this sine squared equals 1 minus cosine squared, I could take this and say cosine squared, oops, not equals, cosine squared minus 1 minus cosine squared. So here, this would simplify to, I've got a double negative here. So this is actually cosine squared plus cosine squared. So 2 cosine squared minus 1. So these are all three different forms of the double angle formula for cosine. Okay, and those are all summarized, on the next part of your paper. Okay, these are all the formulas that we just derived. These are called the double angle formulas. So let's talk about how we're going to use them. Okay, in the last section, we were able to use our sum and difference formulas to find exact sine, cosines, and tangents of angles that we didn't know. That's not super useful for the double angle formulas. Okay, I just want to go through a real quick example. This one's not on your paper of how we could use that, but any angle on the unit circle, if I double it, I also already know that angle. For example, if I double 30, I would be at 60, and I already know that angle. If I double 150, I'd be at 300, and I already know the sine and cosine of that one. But a quick example, I can say the cosine of pi over 2 is the same as 2 times pi over 4. Right? If I write this as 2 times some angle, so then I can look up here and say, well, cosine of 2 times some angle, I could use any form, is equal to cosine squared of that angle minus sine squared of that angle. All right, so then cosine of pi over 4 is the square root of 2 over 2. So we'd have the square root of 2 over 2 squared minus the square root of 2 over 2 squared. So then I don't really need to multiply this out because I can see it's the same thing minus the same thing. We just get 0. And the cosine of pi over 2 we already knew was 0. This was just a more complicated way of finding that. Okay, so we're not really going to use the double angle formulas for something like this. The next example is what we can use the double angle formulas for. So here, I'm given that sine of x is 12 over 3, and that angle x is in the second quadrant. So whenever we have something like this, we want to draw a picture. Okay, so I know that my angle x is here, and then the piece of information I'm given is that the sine, which would be the opposite over the hypotenuse, is 12 over 13. Okay, so I need to find this missing side. Now, we could use Pythagorean theorem, but this is a Pythagorean triple. Okay, if you recognize that this is a 5, 12, 13, right off the bat, I can say that this is negative 5, okay, because the x value would be negative over here. That we do need to recognize that. So now, just looking at this, okay, I can list out my sine, cosine, and tangent of x, and then use those to find the double angles. So we know that sine was 12 over 13. We can say that cosine is negative 5 over 13. And we can say that tangent is 12 over negative 5. So now let's plug or use these to find our double angles. So sine of 2 times x is going to be 2 times the sine. So I'm going to go ahead and plug that in, which would be 12 over 13 times the cosine, which would be negative 5 over 13. So if we multiply all that out, we'll have negative 120 over 169. And I don't think that reduces at all. Then cosine of 2x, we can use whatever form we want. I'll use the first one. I'll do cosine squared. So negative 5 over 13 squared minus 12 over 13 squared. So that'll be 25 over 169 minus 144 over 169. So that's going to end up being negative 119 over 169. And then finally, tangent of 2x would be 2 times the tangent, so 2 times negative 12 over 5 over 1 minus negative 12 over 5 squared. So let's see what this will simplify to. So that'll be negative 24 over 5 in my numerator over 1 So when I square this, it'll become positive. So this will still be 1 minus 144 over 25. And let's see, that would then simplify to negative 24 over 5 over, so this would be 25 over 25, right? If I need to get common denominators to subtract these. So 25 minus 144 would be negative 119 over 25. Then I can rewrite this as negative 24 over 5 times 25 over 119. I can reduce then. If I've got 25 over 5, that would reduce to 5 over 1. And finally, if we multiply this out, negative 24 times 5 would be negative 120 over 119. Okay, so those are our final answers here. Sine, cosine, and tangent of twice my x angle here. Okay, gets us these values. So the other thing that we can do with these formulas is go backwards. Okay, finding the value of something like this. Okay, so this is just looking at this expression and seeing which of my formulas this fits. Okay, well, this actually fits the sine of the double angle formula. So this is actually equal to sine of 2 times this angle. So 2 times 15 degrees. Well, this would end up being the sine of 30 then. And we can look at our unit circle. So let me go back to this slide. The sine of 30, the y value at 30 degrees is 1/2. So this whole expression here is just equal to 1/2. All right. For this one, again, we just want to see which pattern it fits, and it is one of our cosine forms. So this would just be the same as cosine of 2 times the angle over here, 2 times pi over 8. So that would be 2 pi over 8, or pi over 4. So the cosine of pi over 4, if we go to our unit circle, the x value at pi over 4 is the square root of 2 over 2. So this original expression is just equal to the square root of 2 over 2. And we can do an example with tangent as well. So this does fit my pattern for the tangent of a double angle. So this would be tangent of 2 times 22.5, which would be 45. So the tangent of 45, so remember, we haven't really memorized those tangent values. So this would just be the sine of 45 over the cosine of 45. Well, those are the same thing, right? If we look at the unit circle, square root of 2 over 2 over the square root of 2 over 2. So I'll go ahead and write that out. But hopefully we can already see this would just simplify to 1, right? Same thing over the same thing is just equal to 1. So this whole original expression was just equal to 1. All right, so now let's take a look at power reducing formulas. Okay, so these come directly from our double angle formulas. So what I am going to do is just take my double angle formula for cosine of 2x, this form of it, and solve for sine squared. Okay, so I'm going to start by, let's see, let's bring the cosine of 2x over to this side, right? I'm going to end up bringing the sine squared over to this side to make it positive. So what I'm going to do is just essentially switch these. Okay, I'm going to add that over to this side and subtract this over to this side. Okay, then I can divide both sides by 2, and we get that sine squared of x equals 1 minus the cosine of 2x over 2. So this formula is useful if I want to reduce powers, right? If I don't want any squareds in my expression. We can do something very similar to come up with a power reducing formula for cosine. So I'm going to take this cosine of 2x in the form that has a cosine squared in it. I'm going to solve this for cosine squared. So here, I'm going to add 1 over. So cosine of 2x equals, whoops, cosine of 2x plus 1. When I add that over, equals 2 cosine squared. And then just divide by 2, and we'll get cosine of 2x plus 1 over 2 equals cosine squared. Okay. Then finally, for tangent, okay, we want to use the idea that tangent squared is just sine squared over cosine squared. So I want to take the expression that I got here, right, for sine squared. We said, well, that was 1 minus cosine of 2x over 2. And we said that cosine squared was 1 plus cosine of 2x over 2. So I can rewrite this as a multiplication problem, right? Multiplying by the reciprocal. So this would be times 2 over 1 plus the cosine of 2x. The 2's will cancel, and this just becomes 1 minus the cosine of 2x over 1 plus the cosine of 2x. Okay, so those are our power reducing formulas. Okay, sine squared is 1 minus cosine of 2x over 2. Cosine squared is 1 plus cosine of 2x over 2. And tangent squared we can write as 1 minus the cosine of 2x over 1 plus the cosine of 2x. Okay, so let's do a few examples where we just reduce an expression so that it no longer has any powers greater than 1. Okay, so in this first example, well, I can say that the sine of 2x, or I'm sorry, the sine squared of x is equal to 1 minus the cosine of 2x over 2. And then I can say that cosine squared is equal to 1 plus the cosine of 2x over 2. Well, I can multiply this out now. Right? In the numerator, I would need to FOIL or double distribute, right? So I would have 1 times 1 is 1. 1 times cosine of 2x would be plus cosine of 2x. Negative cosine of 2x times 1 would be minus cosine of 2x. And then negative cosine of 2x times positive cosine of 2x would be minus cosine squared of 2x. And that would all be over 4 then, if I multiply those together. Well, I can cancel these out, right? Positive and negative of the same thing, those will cancel. And then I will just be left with 1 minus the cosine squared of 2x over 4. Well, we still have a second power here. I'm going to need to use a power reducing formula again. Okay, so I'm going to say that this is 1 minus. Now, cosine squared is 1 plus the cosine of 2 times whatever the angle was. Okay, in this case, my angle was 2x. If I double that, it will now become 4x. Okay, so we need to be careful here. This means 2 times whatever the angle was. So here, the angle was 2x. So it's going to become 4x. So this will be 1 plus the cosine of 4x over 2. And then that'll still all be over 4. So the first thing I can do is make this 2 over 2 to get common denominators here. So I'll have 2 over 2 minus 1 plus cosine of 4x over 2, and then that's all still over 4. So here I've got 2 minus 1, so that would just become 1. And then we need to be careful. This negative sign would also need distributed to the cosine of 4x. So this will be 1 minus the cosine of 4x over 2 all over 4. So this would just become 1 minus the cosine of 4x over 8. Okay? So then let's try one more. Okay, let's try this 4 sine of x cosine of x times 2 cosine squared of x minus 1. Well, these, okay, I can see that this fits the pattern of one of my double angle formulas. Okay, 2 sine of x cosine of x is just equal to sine of 2x. So I can say that this part here is equal to 2 times the sine of 2x. Okay, because we said sine of 2x is 2 times the sine of x cosine of x. So I just need to multiply that by 2 again. Then here, 2 cosine squared minus 1, well, that also fits one of my double angle formulas. Right? That is cosine of 2x. Right? So uh, technically, we have already reduced it to where there are no trig functions of power greater than 1, but we can actually go one step further here. This, yet again, fits my double angle formula for sine, right? 2 times the sine of some angle times the cosine of some angle. So this is actually just the sine of 2 times that angle. So 2 times 2x, which would be 4x. So I can say that this whole thing just reduces to the sine of 4x. All right. So that is it for this video. The final question is going to pop up asking you what questions you have.